AI can write pristine code, pass the bar exam, and generate hyper-realistic art in seconds. But ask that exact same intelligence to pick up a simple glass of water, and it often shatters it. The issue comes down to how traditional vision language models see the world. To them, an image is a flat grid of pixels, containing no internal information about depth or volume. This flatness creates a physical blind spot. The AI can look at a table and tell you what an object is, a cup, an apple, a spoon, but it cannot calculate where that cup is located on the z-axis relative to the objects around it. That lack of spatial awareness makes multi-step, real-world tasks, what roboticists call long-horizon manipulation, like cooking a meal or assembling parts, impossible. Navigation requires a constant perception of physical distance. Mastering the third dimension is the mandatory hurdle AI must clear to transition from a digital tool into an autonomous physical agent. To solve this, researchers initially built mathematical bridges between the 2D image and the 3D world, using models like N3D VLM to perform a technique known as 2D to 3D lifting. By taking standard images, estimating depth maps, and applying camera intrinsics, individual pixels are calculated and extruded backward into virtual space. These points resolve into a dense 3D point cloud, giving the AI a topological map of its environment with measurable dimensions. But mapping the space is only half the battle. Once the AI knows where things are, it needs to understand the physical rules governing the objects it plans to touch. To do that, scientists developed structured 3D object knowledge bases. These libraries teach the AI graspable affordances, cataloging exactly where an object's center of gravity lies and exactly where mechanical fingers should be placed to maintain a stable grip. Armed with a topological map and a geometric knowledge base, the model explicitly calculates physical vectors and clock directions inside a simulation before it ever attempts to move. By combining flat pixels with these 3D reference libraries, researchers gave robots the spatial blueprints required to plan complex movements. These lifting techniques are effective, but they require multiple specialized subsystems to operate together. Recently, researchers began looking for a simpler, more scalable way to teach AI about space. Meta's VLM3 research recently identified a simpler path. Standard text-predicting AI models appear to be native 3D learners. The first step is mechanical. Resizing images so focal lengths are identical across every picture eliminates depth ambiguity without new software. Second, 3D pixel locations are translated into text brackets. This formats spatial data into the exact language the standard model already reads natively. With the lens normalized and the coordinates formatted as text, standard models can calculate depth and camera poses with accuracy that matches specialized expert systems. Spatial intelligence emerges when physical space is translated into the sequence-based language these models were originally built to process. This native 3D capability drastically accelerates the timeline for general-purpose robotics. Improving the robot's physical skills now becomes a matter of scaling up standard training data. Models like spatial VLA serve as proof of concept, allowing robots to execute complex physical tasks in dynamic, real-world environments without task-specific fine-tuning. This data from tables I and II illustrates the impact of this spatial understanding. In both simulated and real-world robot tasks, models with 3D awareness achieve significantly higher success rates when matching visual conditions and navigating environmental variations. Scaling these natively 3D models bridges the gap between high-level reasoning and the coordinate-perfect accuracy required for physical interaction. By naturally mastering the z-axis, artificial intelligence has broken through the glass of the 2D screen. It has gained the capacity to navigate, reason about, and physically interact with our reality.